Hello, class. My name is Andre Williams. Today I'll be giving a presentation on C-Store, a column-oriented database management system. This was a proceeding of the 31st International Conference on Very Large Databases. Okay, so what is the problem discussed in this research paper? Before we get started, let's do some housekeeping and discuss some of the keywords. So the main keyword is OLTP, which stands for Online Transaction Process. It refers to transactional workloads that typically involve frequent writes and updates to the database with short-running queries accessing small amounts of data. So essentially, lots of small, fast queries that read and write data. So let's think of some examples of OLTP applications, or like order processing system, retail sales, banking transactions, airline reservations, etc. These databases for these systems need to efficiently handle large volumes of concurrent transactions, so quick reads and writes of small amounts of data. Now, what is the problem? This paper addresses the problem of efficiently supporting both OLTP style transactions and analytic ad hoc queries in a single database systems. Many existing systems are optimized for one or the other, but not both. The problem being addressed is clearly stated in the introduction and abstract. The authors state that most commercial database management systems are optimized for OLTP workloads and frequent writes, while data warehousing and other analytics systems are optimized for analytics and reads. So think of OLAP, which we'll discuss later. Their goal is to design a system that can excel at both simultaneously. The author highlights that a key issue is a tension between updating data structures efficiently to support transactions versus optimizing them for analytic queries. Existing solutions tend to focus on one or the other. Another key issue raised is scaling out across multiple nodes or servers. So most OLTP databases don't focus on distribution systems to efficiently handle large amounts of data. Okay, so why is this research important? So this problem was new at the time. This paper was written in 2005. Um, it was relatively new. While separating OLTP and analytic systems have existed for a while, trying to achieve a single system optimized for both workloads is a new area of research, especially at a large scale. Overall, this is important, timely, and novel. Both academically and practically, there are good reasons to care about the ideas and results presented in this paper. The potential impact is significant if the system works. Um, so, some of the bullet points here: separate databases add complexity and overhead, and that translates to money, dollars, cost. Most companies don't like that. Um, Exponential growth is another reason why this is important. It becomes increasingly difficult to handle it as the data grows. Um, Real-time analytics. Most companies want to process and analyze that data in real time. As soon as they get into their system, they like to see the results or see some type of computation. Lastly, I mean, this is a challenging problem, so it's very important as it can advance the state of the art database systems that we use today. Okay, so why is this challenging? We will just hit the bullet points here. So first off, storage layout trade-off. So role-oriented storages are optimized for OLTP. Columns are more column-oriented or more optimized for OLAP or analytics. Choosing a single layout that works well for both is tough. Indexing trade-off. We know that looking up data that's by index is more efficient than doing a full table scan, but they're both different. Query optimization. It's hard to build a optimizer and execution engine that can handle both OLTP lookups and OLAP analytics. concurrency control mechanisms like locking that ensure transactional consistency can limit parallel computing, data loading. Loading new data efficiently for both workloads is tricky. Hardware utilization, optimizing, leveraging modern hardware with large main memory, main cores, solid state drives for various workloads is challenging. And lastly, distributed architecture. Scaling out of many nodes in a cluster while keeping both workloads efficient is extremely hard. Okay, so what are some of the limitations mentioned in the related works? There were a couple papers discussed in the related work section. One of the limitations is role-oriented databases. So row by row storage, as we know, is more efficient for quick access of data like lookups or like retrieving details about a specific customer. Um, Another topic is, analytic queries often need columns, right? They need columns of many rows, and loading entire rows from disk to memory results in wasted I/O, and cache usage is only needed for some of the columns. Um, Aggregated queries, which often group records based on a subset of columns, perform poorly because entire rows must be loaded before filtering. Another issue is they lack optimizations like column level compression, which is often used in like Redshift, Amazon Redshift. Another limitation is column oriented databases, right? What are their limitations? So column storage optimizes analytic queries by allowing loading only relevant columns from disk and applying column level compression. But row-oriented inserts and updates require reconstituting entire rows by reading values from many separate columns, files, or blocks. So replacing an entire row across all the columns. Single row lookups may require hitting multiple column files, resulting in high latency compared to row stores. Column oriented data warehouses are not optimized for concurrent and locking during high volume transactions, modifying data. So think of like Christmas time when you get a lot of sales, high volume. And last limitation of column oriented data warehouses is overhead for maintaining row level versioning information during updates, which can be, once again, costly money. Yeah. Right. So, what is a novelty? Once again, this paper was published in 2005. It is now 2024. At the time, there were no previous systems that had fully solved the problem of optimizing both OLTP and analytic workloads in a unified architecture. Since then, we've had new research or new papers that show potential of handling is like this, like HTAP, which is a hybrid transaction analytic protocol. This report was released in 2014. It's an emerging application architecture that breaks the walls between transaction processing and analytics. It's a data architecture that joins OTLP and OLAP workloads. This particular paper introduces new techniques to allow excellent analytics over primarily column-oriented architecture while enabling transactions via a second row-oriented storage. So, what are the contributions here? I'm running short on time, so I'll just run through this quickly. Overall, this paper makes multiple novel contributions in areas of database architecture, storage layout, concurrency control, query execution, optimization to achieve the goal of high performance, hybrid transactional analytical database systems. It extends previous work in multiple dimensions. So, what is the validation methodology used here? They use the common practice of benchmarking. They use a simplified TPCH benchmark, which is an industry standard decision support analytics benchmark. So this benchmark includes three tables, line items, order, and a customer. These are representative of analytic schemas. The workload consists of 7 TPCH style queries focused on aggregates, join, grouping, typical analytic queries. The system compared both, it compared C-store, the proposed algorithm used here, which is in this paper, which is a hybrid transaction analytical system. Row store is a popular commercial row-oriented OLTP database. Column store, which is a popular commercial column-oriented analytic database. The measurements, the metrics measured is were query latency, how long each query takes to execute on each system. This directly measures analytics query performance. The methodology. This experiment controls for storage space used in each system, which was 2.7 gigabytes for space constraints, more for unconstrained. Each system schema is tuned based on this architecture to optimize performance. Two scenarios tested, space constrained and unconstrained space for commercial systems. And yeah, that's it for this slide. So I want to go over some of the strengths and weaknesses of the validation methods used in this research paper. So one of the main strengths was the usage of the TPC-H. This tests a standard workload representative of real-world decision support queries. This provides a solid benchmark to measure analytic performance. Another strength is directly comparing query latencies. Gives a clear metric for assessing the performance impact of the architecture versus other systems. Another strength is tuning each system's schema and controlling storage space used ensures the comparison between CStore and the other databases is fair. Another strength was testing both a space constrained scenario against an unconstrained scenario. Some of the weaknesses, the paper states their right optimized components are still in progress. So there's no full end-to-end transaction performance that we could test. Only analytic queries are tested so far. To fully validate their claims, OLTP workloads need to be run, testing latency, throughput, concurrency. Another weakness is additional experiments could provide a more thorough comparison. So they could have tested scalability on bigger data sets, varying the query types beyond TPCH, or exploring different schema designs. Lastly, one of the weaknesses, they could be more detailed, providing on the schema tuning process and specific schemas used for each system. And that is the end of my presentation. I hope you enjoyed. I hope you learned something. And until next time, cheers, classmates.